So I would like to go over two more examples of acid-base reactions. And what I like to go over in this video is how acetic acid can be deprotonated and how it can serve as a ligand for a transition metal compound. And then we'll look at how acetylacetone can do the same, where it can be deprotonated and serve as a ligand for a transition metal compound. So imagine we have in solution, we have our acetic acid, and we treat that with a base. So for a base, let's just use a hydroxide anion. So what can happen is we can have our hydroxide anion pick off a proton from the acetic acid, and this will generate an acetate anion, and it will also generate water. So it'll also generate water. So we can define a few things here based on what we've learned from previous videos. So we could say in this expression, the acetic acid is the acid, the hydroxide ion is the base, the acetate anion is the conjugate base, and the water is the conjugate acid. So let's look at this conjugate base. This conjugate base right here has a resonance structure as follows. So we can imagine pushing electrons here, pushing them up here, and then we make another resonance structure of our acetate anion. So one way we can think about an acetate anion is we can think about it as such. We can think about a delocalized negative charge between these two oxygen anions. So you can think about each of those oxygens having a negative 1/2 formal charge, or you can think about in total, what I like to think about in total is that there's just a minus charge on this acetate. So what happens is if you have a metal, let's say you have a metal and you react it with an acetate anion with that delocalized negative charge, what can happen is that the metal can bind to both of the oxygens on this acetate anion. And this is an example where the metal is acting as a Lewis acid. So remember, Lewis acid accepts electrons. So we think about the metal accepting the electrons from the oxygens. So the metal is acting as a Lewis acid. This acetate anion is acting as a Lewis base. And this is a common thing we'll actually see in coordination chemistry, where we have the acetate being bound to the metal at 2 oxygens. So another common ligand for transition metal chemistry is this acetylacetone. So acetylacetone can form enolates, right? Because we have hydrogens that are alpha to a carbonyl group. So here is our acetylacetone with all of its acidic hydrogens. Now, all of these acidic hydrogens are not created equally. The hydrogens in the middle, let me use a different color, let's say green. So the hydrogens in the middle right here, because they are adjacent to two carbonyl groups. These are going to be the most acidic. So if I react this acetylacetone with one equivalent of hydroxide, I am going to be able to deprotonate that hydrogen or the other green hydrogen, and I'm going to make my anion that looks like this. So here is my deprotonated acetylacetone. This is often referred to as the ACAC ligand. We can imagine certain resonance structures for this. And like the acetate ligand, we can think about this as, there's just a delocalized charge around the two oxygens and even the carbon, because if we have a negative charge here on the carbon, negative charge on the oxygen, negative charge on the oxygen like this. So the way the ACAC ligand can interact with the metal is as follows. So imagine if we have a metal and we have our ACAC ligand like the acetate anion, the metal will interact with this Lewis base. So the metal here is acting as a Lewis acid. It's accepting electrons. The ACAC ligand is acting as a Lewis base. So think about the lone pairs on this oxygen just being able to pop onto the metal center. And then we get our complex. So here we have the metal coordinating to two oxygen atoms. And remember, in this reaction, the metal is acting as a Lewis acid and the ACAC ligand is acting as a Lewis base.